Okay, thank you everybody for coming. So today we're going to talk about JupyterLite. So maybe a quick word about us. So it's me, Jeremy, Ian, and there is also Thorsten, who is in all of this. He contributed a lot to the materials and also to the actual tech behind all of this. But he couldn't make it today. So yeah, so we're all working at Constack. Constack is deeply involved in the Jupyter ecosystem and also the package management with Conda and Mamba and JupyterLab. So you might ask, what is JupyterLite? So JupyterLite is a JupyterLab distribution that runs entirely in a browser, backed by in-browser language kernels. So if you have used Jupyter before, you can see it like this. So you have like a user that uses a browser. The browser makes HTTP requests to a server, and then there is this kernel system in the backend, and with all of this we have a notebook file that we can edit. So you have multiple components running in different places. But with JupyterLite, it's almost the same, but everything is in the browser. So what you get with this is a lightweight Jupyter frontend. So it means that you don't have to set up Python. There is no command line to run. There is no need to install Python packages locally. And you can host everything as a static website. You go to a URL, and it loads in just a few seconds. Because behind all of this, you have something called the JupyterLite CLI. And you can see it as a static site generator, a little bit like Jekyll for making blogs. So when you run the command, you get files on your disk that you can then host somewhere. So it's like HTML, CSS, JavaScript images, and WASM files. Because of this, it's very easy to just deploy it anywhere where you can host static files. The common examples are GitHub pages, GitLab pages, but then you can also consider platforms like Versal or Netlify or even S3. So JupyterLite is not really like something fancy. It's just taking many different projects and putting them together. So it's really built on top of the JupyterLab ecosystem and the Jupyter protocol. And it's also compatible with popular libraries like Matplotlib, BQplot, and many others. So we mentioned WASM before. WASM is for WebAssembly. And WebAssembly is now part of the browser kind of default languages that you can have in a browser. So with HTML, CSS, JavaScript, and now there is also WebAssembly. And the trick with all of this is, so the main implementation of Python is written in C, and C can be compiled to WebAssembly. So you can now have Python in WebAssembly. It sounds very simple, but it took years to arrive to this state. So yeah. Thanks to all of this stack and tools, you can have interactive computing in a browser. That means using different Python kernels and using different visualization libraries like Matplotlib, PyWidgets, Plotly that we saw before. And because it can be easily hosted anywhere, you can also embed it easily with iframes. So here we have a screenshot of Python REPL on a blog built with Jekyll, and you can see it's just a few lines of code to inject in your blog if you have one. But you could also include the whole JupyterLab UI if you want. So here, the presentation is HTML. We use this iframe trick to embed the full JupyterLab, and you can also run it here. Many projects have adopted this for their docs and websites. So if you go to numpy.org, you can find the Python REPL, but also on simpy.org. And you can also use JupyterLite things to do it on your own docs. To make this a bit easier, there is a template that you can use on GitHub pages. And once you have it, then you will have a couple of files. You can directly work with your files in the browser. So there is JupyterLite for the notebook-based UI. You might have heard about Voila to turn notebooks into web applications. And now there is also Voici, which you can turn notebooks into static web applications. So here I have a quick demo. So you have your notebook, edit it in a JupyterLab interface, and then it's just a matter of using a different renderer that we call here the WASI renderer. And it says starting up the kernel, but the kernel is actually starting up in the browser. So it needs to download a couple of assets. So it takes a few seconds to load, and then it executes the cells. And then it just shows the outputs of the cells, which is the default behavior in WASI. You can also show the code if you want, like in Voila. So this is very convenient to share something with others, and without having to care too much about setting up a server. If you're looking for inspiration, there is the WASI gallery. And if you are already using WASI, you can also contribute your example to the gallery. That would be really appreciated. So small wrap-up on the strength of JupyterLite. It's very easy to deploy and scale because it's just static files in the end. That makes it a good tool for interactive computing in a browser and make it accessible to many, many people. It's a bit simpler for users because they don't have to open a terminal to install Python or go to a website to download Python. So we see that in educational use cases, it's used more and more nowadays. And because you can have all of this self-contained into some kind of archive on disk, you can also see it as a reproducibility time capsule that will resist the test of time. So web standards are here to stay. And the idea with this is that you can create some kind of archive of your work, or your research, or anything else. And normally, in a few years, 10 years, 15 years, it will still work because as long as you have a browser, of course. So there's been some work recently on several aspects of JupyterLite. There's been some work into getting the AI code completions in the JupyterLite UI. Real-time collaboration also, like we saw in the previous talk. And work on an in-browser terminal, because that was one of the missing parts of JupyterLite. So if you go to JupyterLab, you have a terminal, you can list your files and so on. But we're going to see a nice demo right after. So here, I wanted to show you quickly some progress on AI code completions in JupyterLite. So there is already a project called JupyterAI, but it requires a regular JupyterLab deployment. And we've been experimenting with a similar approach, but for JupyterLite. And instead of having a backend, you would directly talk to the AI provider. So you could use models from OpenAI or from Mistral or from the Google as well. So still a little bit of work in progress, but the APIs are here now in JupyterLab, which means we can start thinking about this a bit more. RTC, so with WebRTC, you can have peer-to-peer collaborative editing. And here is the same, we're using the GitHub pages deployment of David, who talked about collaboration this morning. And you can collaborate on files in your browser without having to manage a Jupyter server entirely. Now, let's talk about the terminal.
So yeah, as Jeremy said, JupyterLab has a terminal which connects to a real shell that runs on the server, so a bash shell, Z shell, whatever. We haven't had that within JupyterLite, but recent work, we're starting to add some form of support for that. Screenshot on the right-hand side. It's very early stage work in progress. Some things that are easy don't work, and some hard things do, strangely. I do have a video of that, but I'm going to bravely try a live demo. So a local deployment of JupyterLite, big enough font. I open a terminal. Let me make it a bit bigger. I can see it. So I can list the files. These are the same files that are displayed on the left-hand side in the file view. So I can, I can write something to a file. That file appears in the file view. Sure enough, the contents are correct. I can delete the file. Fairly standard file dealing with files. grep command, for example, so we can look for a grep in a file of months. We can then pipe it through sort. Fairly sort of standard stuff. If we do a uname -a, so tab completion there, it tells us we're not running in like a real computer, we're running in the web browser, we're running on Emscripten using WASM32, WebAssembly 32-bit. One of the difficult things we can do, surprisingly, is we can actually run Lua, the programming language, as an executable within the terminal shell itself. So I have a small file here, which is a Lua program, just to calculate and print some factorials. And I can run it. So I can say Lua factorial 3, and so on. Thank you. And we'll preempt the first question we would normally get is, oh, will I be able to run Python this way? And at that point, we start getting a bit worried because Lua is like a single executable with all the programming language together. But in Python, we expect to be able to use NumPy and Matplotlib and all these other packages which make Python sometimes awkward to deal with because of the packaging system. So to have Python running just using the Python standard library this way would be pretty easy. But if we want to start adding other packages, then we have to have some implementation in WebAssembly of a package management system. And that's probably going to happen at some point, but maybe not in a hurry. Right. Back to the slides terminal. Right, the talk is about 4 tools. We've only really covered JupyterLite so far. There are 3 others that sit behind the scenes, make it all possible. And if you understand a little bit about those 3, it will make the whole experience a bit more pleasant for you. So they are Xeus, which is a class of programming language kernels, Emscripten-forge, which we use to build and upload packages to make them available. And Mamba is the tool that works with Emscripten-forge as the package manager to help you resolve and install of those packages. We'll go through them. So firstly, we'll talk about Xeus, but I'll take a step back because we talk about kernels all the time, and maybe that's slightly ambiguous. What is a kernel? So in JupyterLab or JupyterLite, you would click on the launcher button to start Python, and that will create an instance of Python running somewhere. Could be a different computer, could be locally, whatever, depends. So that's an executable that takes in Python code, i.e. text, and does weird and wonderful things with it. It does not know it's running within Jupyter. Well, it can do, but it's not fully aware of what's going on. So when you put some code in a code cell and press the run button or return, that code is sent to the programming language interpreter to run. That happens via a bunch of messages, and the correct name of those is the kernel protocol. So the word kernel really relates to this definition of the kernel protocol that allows us to send information to the Python instance and get results back. So I always think of the kernel as being like, as drawn here, as a wrapper around the Python instance or the programming language instance, although quite often we would use the word kernel to represent both that wrapper and the programming language inside. So yeah, Python kernel is Python running wherever, but able to understand the kernel protocol messages so Jupyter can talk to it. One of the confusing things about JupyterLite is there are 2 different Python kernels. Most of the time, you can probably use either, but again, it's worth knowing some of the differences because it can affect you. So on the left, we have a PyData kernel, and I imagine everybody's heard of PyData. So that is, as Jeremy said, the C implementation of Python compiled via the PyData toolset. And somebody, my colleagues, have written a kernel wrapper for that so it can be talked to in the Jupyter normal way. Now, we primarily use Xeus because it's a slightly different design. So that's really a framework that supports multiple programming languages using the kernel protocol. So it's written in C++, but like implementation detail for you all, really that's an abstract. Xeus is an abstract base class that implements the kernel protocol, and it has abstract functions for things like execute code. We will have a derived class called Xeus Python kernel, which gets all of the kernel protocol messaging for free from the base class, and all that does is have concrete implementations of functions like execute code. So this way, for a relatively small amount of effort, because of the architecture, we get to have a Loire kernel, a Python kernel, an R kernel, which is on its way in JupyterLite, already exists in JupyterLab. So it's, if you like, this is really about the scope of what we're aiming for. So PyData is only concerned with Python, absolutely fine. Xeus is looking wider than that, at the bigger picture. Other programming languages are of interest to people. What are the differences between the two? Well, one of them I've just been through, but that makes no difference to you as a user, I should say. The main difference actually is how they're built. So PyData is pip-based, Xeus is conda-based. That will be important in the next slide. With PyData, you get like a distribution with lots of included packages. You can also install extra packages at runtime, and it does sort of the whatever network connection to get those from the PyData repository. Xeus works in a different way. You have to have pre-installed packages like a virtual environment you would define in advance, and you're restricted to the packages that are within that virtual environment, but they're sort of served in a different way. There are some other subtle differences like availability of time sleep that either doesn't matter to you or is fundamentally important depending on where you sit. Now, Emscripten-forge and Mamba. Lots of our problems are related in the Python ecosystem with building packages, getting them distributed, installed on machines, running, and being in a web browser makes it worse, essentially. We still have the same sort of problems, right? If you design a new Python package and you want the world to use it, what you normally have to do nowadays is release it two different ways. Firstly, so people can pip install it, and that would have to go on PyPy. You would also have to do some sort of conda-based building of the packages. Normally, you would put that on Conda-forge. It may go under the other conda-based repositories too. It's unfortunate that there are two here. That is mostly historical. Nowadays, there's a little bit of politics there too, which we shan't go into too much. But I should say that the conda-based toolchain, so yeah, pip-based toolchain really only deals with pure Python packages and compiled packages that have a Python interface. So they're only really thinking about use from Python, a bit like PyData is only thinking about use from Python. The conda-based toolchain considers the existence of other programming languages, so those packages are not just Python-based. It includes things like, so if you wanted to use a PNG library in your Python or R packages, then there is just like a PNG library that's pure C, I presume, and is compiled on Conda-forge. You can make use of that to make your work easier, because someone else has done that for you, and we have a single implementation of that PNG library that can be used across multiple packages. Right. For a pure Python package, we would call that no arch. All you've got to do is get those Python files to your end users. Doesn't matter what platform they're on, it works in the same sort of way. If it's compiled, so C, C++, Fortran, Rust, then you have to compile them for the different platforms. So Linux, macOS, Windows are supported on PyPy and Conda-forge. Now, for JupyterLite, our platform is called Emscripten-WASM32. So Emscripten is the tool set and the compilers to generate WebAssembly code. WASM stands for WebAssembly, and 32 is 32-bit. 32-bit code is still alive and well in 2024 in this particular way. PyPy does not support the Emscripten-WASM32 platform, so PyData has its own dedicated build system and serving of those packages. Similarly, Conda-forge does not understand Emscripten-WASM32 platform, so Emscripten-forge is really a smaller version of Conda-forge just for WebAssembly. That's all it is. And I haven't mentioned Mamba, but the Conda-based toolchain, that includes multiple tools. That's Conda, the famous one, but Mamba as well, and nowadays Pixie, same sort of thing. Conda, again, does not support Emscripten WebAssembly platform, so we use Mamba because Mamba does. This bottom row here, we'd like to get rid of it. There is, in fact, work underway both in PyPy and CondaForge to be able to include the Emscripten WebAssembly platform within them, and then this slide becomes a lot easier. The bottom row disappears entirely. Right. One question we get is, how do I use a particular package in JupyterLite? And this sort of covers how you would create one from scratch or how you would check if it already exists. Right. If it's a pure Python package, then it's going to be fine. There will be a no-arch wheel in PyPy and a no-arch package in CondaForge, depending on if you want the PyData or Xeus approach. Because it's just Python, that will run in the WebAssembly implementation of Python. Fine. If it needs compiling, if you want it to be available for PyData, there's a link here for where you would have to create a recipe. If you want it to work in Emscripten-forge, so with the Xeus kernels, you have to have a recipe in Emscripten-forge. So you would open a PR or maybe an issue and ask for some help. Generally, you would get some help in implementing those recipes, and normally you'd be copying and pasting somebody else who had done a similar build system. Let's bring it all together then. How do you create a JupyterLite deployment? The most easy thing to do is to follow one of our two demo repositories. If you want to use the PyData kernel, then there's one link. If you want to use the Xeus Python kernel, there's a different link. They basically do the same thing, slightly different way. What inputs do you require? Firstly, what packages do you want to be available within the Python kernel running in JupyterLite? What contents do you want to include? Notebooks, data files, whatever. And finally, there has to be a build environment, which is local virtual environment or Conda environment containing JupyterLite core, which has the command lines tools to build the deployment. So in this slightly busy slide, this is the whole thing. So this is how I would create a local deployment to use both Python kernels. So we've got a build environment on the left, we've got an environment file on the right, and the sequence of commands down the bottom. So the build environment, the important thing there, firstly, JupyterLite core. So this will run on your computer. So for me, this would be a macOS platform build environment. JupyterLite core is the important thing. We've also added the PyData kernel and the Xeus kernel. There is some magic that goes on here. When you build the JupyterLite deployment, it identifies you have these present, and it makes sure it includes what is necessary in the final deployment for you. The one extra piece of magic, if you're using JupyterLite Xeus, it expects to find a file called environment YAML, and this is where you would list the Emscripten-forge packages that you wish to include in your Xeus Python implementation. So here, I've just got Xeus Python, I've got matplotlib and IPyMPL for interactive plots in matplotlib. Interesting observation here then, it starts to make sense. So there are two channels. There's the Emscripten-forge channel. This is where the compiled WebAssembly packages will have to come from. If it's a pure Python package, though, it comes directly from CondaForge. That's why we've got the two environments there. And the commands are relatively easy. We create a virtual environment, in this case, a Mamba environment. We build the site, and we serve the site. The important thing about this slide, it mentions JupyterLite, it mentions Xeus, it mentions Emscripten-forge, and it mentions Mamba, so all four tools that the talk is about. Quick summary of improvements in the last year then that we haven't mentioned so far. There's actually a better build system, which is much easier to use, called Rattler build in Emscripten-forge. It just makes things easier, won't affect many people. And we've already mentioned the experimental terminal. Looking ahead, there is an R kernel being written as we speak by somebody in the room. That shall hopefully be available soon. And I did mention the proposals to include Emscripten-forge within CondaForge and the PyData build into PyPy too. One of the big changes we would like to include is to allow Xeus kernels to install packages at runtime, a bit like PyData does. That would be quite a big improvement for the ecosystem. Which brings us to the end. Thank you very much. This is a presentation in a GitHub repo. If you take a photo of that, whatever, then you can see our slides as presented here. I guess we have time for questions, or you can find one of us later on today or tomorrow. Thank you.
Thank you. So, yeah, there's 5 minutes for questions, so anybody wants to ask something? Yes, okay. We'll start by.
Now that we have a terminal, how far would we be to have Git running in that terminal?
Sorry?
How far would we be to run Git inside that terminal?
So Jeremy warned me this would be one of the first questions. You're going to have to wait. Some things are very difficult, some things are really easy. So Git is a great example. Half of Git we could probably have tomorrow. So the bit where you have a local repo, checking stuff in, checking stuff out, making changes, absolutely fine. But then the next half, I'd like to clone a repo, so network access, fine. But then, I want to sign it with a GPG key, and I want to send it via SSH. So now we need an SSH implementation and a GPG implementation, and that's a lot more work than the key bit of Git we wanted at the beginning. Mostly, I'm personally aiming for maybe only 50 or 60% coverage of the JupyterLite terminal, things that are easy, because it does get exponentially difficult beyond that. But I don't want to say no to you, but I cannot say yes.
Almost. Any? Yes. Yeah.
Thanks. So it's still a question about the terminal. You're in the WebAssembly sandbox, so you don't have access to the file system, or maybe a subpart of it. For instance, you mentioned being able to use SSH, but my keys are outside of what the browser is supposed to see. So I'm just wondering, how does the terminal interact with the file system, basically?
So the files you see on in the terminal are the ones that are also listed in the JupyterLab file browser here. And by default, they are stored in the browser storage. So it's not like files on your disk. It's just, so the default content manager in JupyterLite stores the files in the browser storage in IndexedDB, to be more precise. But this is actually configurable and could be changed by another extension. So we could imagine fetching the files from a different location and then being able to work on them from the terminal. Yeah. So those are two separate things. Yeah.
Okay, another questions?
Hi. I was wondering, what are the challenges that you foresee by moving both PyData to PyPI and Emscripten-forge to kernels-forge? Because, like, it might be my ignorance, but PyData is kind of a distribution, right? How does that fit in the PyPI model?
I don't think there's any intrinsic problem with two, except it just makes the whole thing less accessible for people when they start out. Because why do we need to? Why is there a choice? Why do they work in a different way? I guess there's always going to remain two, but I think they will converge in how they work to some extent. So at the moment, the package management is entirely different between the two, and that's the problem. But when you can dynamically install Xeus packages in the running kernel the same as PyData, then for 99% of use cases, it doesn't matter which one you choose. You don't need, so then the problem is removed, unless that situation changes. But yeah, I think it's mostly a extra hurdle when people start out.
Time for, okay, another question, last one.
Hello, thanks for your talk. I had a question. What do you know about, is it possible to access to GPU for computation when you are in a web environment? I mean for computation and rendering.
Not yet. It could be interesting, I think, especially with the web GPU. So you could have even training, maybe, of AI models locally in a browser. But I don't think there's been some progress on that so far. That would likely happen maybe as part of the PyData project or a library. But so far, I don't think there is any work on that at the moment. Even though I think it would be really, really useful also for inference locally.
Okay, so I think we can stop here. So we can, thanks again, Jan and Jeremy.